So what I'll be speaking today about is learning, but in the context of physics. So of course, in physics, people have been always been using data, a lot of data these days. But I'll be taking a slightly different point of view, which is not about how do you use data in physics, but whether you can really learn physics from data. In other words, suppose that you have some limited priors and you have a lot of data. Can you infer some property about physics? You know, it's the kind of question that you may think a mathematician would ask to get rid of all his physics colleagues, given that he knows little about physics, so just limited priors. But it's not the only motivation for trying to raise that question. If you think about it, there are a lot of structures in the world which are, in some sense, learning physics from data. If you take the case of electric fish, as you know, they emit an electromagnetic wave. There is on their body detectors on which they can measure the potential. And they basically solve the inverse electric tomographic problem. From these measurements, they are able to infer distances, conductance of objects relatively far away. And the fact is they can do that much better than what we can do from Maxwell equation by trying to invert Maxwell equation. There has been a lot of experiments on these fishes to see what's the precision of their inversion. And the thing we know is that it's much better than what we actually do. So the question is, are they learning some physics? And what kind of physics do they learn? They learn from data. Maybe there's some prior given by their brain, but can we consider that these are relatively good physicists? So one may say, no, they don't learn because, you know, they don't know about causality, they don't know the fundamental equations. Yes, but they do much better than we do. So, okay, they don't learn, but they're not so bad. So let's try to understand that kind of question. At least that's the kind of thing that I would like to speak about today. So if you think of learning in the traditional framework, what is it about? So it's about getting data, and the specificity of learning in high dimension is that the data that I will always write x here is a high dimensional vector. So it can be an image. So an image has about 1 million pixels. So you are in dimension 1 million. And the point of high dimensional learning will be to try to learn a function of x. So in, for example, image recognition, this function of x can be a label. This is an image of a cat or of a dog or whatever. But if you are in the context of a physical problem, x will describe the state of the system, and f of x will be some physical property associated to the system. For example, you may want to learn the energy of the system. So associate to the state the energy. If you know the energy, then through derivatives you have access to forces. If you can indeed learn energy, then one may consider that you've really been able to learn some level of physics. And we'll look at that kind of problem that can be looked at either in astronomy, so x would be, let's say, the distribution of mass in a galaxy, or at an infinitely small scale, quantum chemistry, where x would be the position of the atoms and their charge. So what we'll look at is rather the context of quantum chemistry. Now, one of the things that is absolutely clear in physics is that symmetries play a fundamental role. If you know the symmetries, you can infer the Lagrangian, and then you can basically compute all the important physical quantities. One thing that I'd like to stress through the talk is that learning is also deeply related to the notion of symmetries. And in that sense, high-dimensional learning and physics are not so far apart. The other type of learning problems are what are called unsupervised learning. In that case, you don't want to learn a function from examples. I hadn't stressed before that I had an example. Let me stress that point. I have to learn an example xi for which I do know the value of the function that I want to estimate. So this is called supervised learning. And unsupervised learning problems are more related to problem in statistical physics, where what you want to do is to learn the probability distribution of your data. And the data, again, lives in a high-dimensional space, so you have a very high-dimensional function p of x here that you want to estimate. And you want to estimate that given few examples. So, for example, here you have a classical problem of understanding turbulence. You have examples, so these have been produced by a team with whom I'm working at École Normale Supérieure in cosmology, astrophysics. So these images correspond to about 100 light years width, and they represent the density of gas of a mix of helium and hydrogen, which can collapse and form stars or structures like this with very strong electromagnetic fields. So what we'd like to understand is what is the probability distribution which gives rise to that kind of structure. So we know very well that that kind of problem are horribly complicated. From a mathematical standpoint, the understanding of turbulence hasn't changed so much since the first publications of Kolmogorov in the 1940s. We still don't understand how to specify such a high-dimensional probability distribution. So unsupervised learning would aim at building such models from realizations. Now, the reason why these things are extremely difficult is, of course, because we are in very high dimension. So the kind of thing that you cannot do is, for example, build histograms, because the number of histogram beans, if you are in dimension d, grow exponentially like the dimension. So if you would like, supposing that you only know that your probability distribution is locally regular, to estimate this probability distribution, you can prove that whatever metrics that you'll be essentially using, if you want an error smaller than epsilon, the number of data that you need will have to grow exponentially fast with the dimension. So that's called the curse of dimensionality. That basically says you cannot learn in high dimension unless you have a very strong regularity on the function that you want to learn, and you have some prior. So in learning in general, the problem will be to understand the nature of this regularity, what kind of priors you can have, and how to use this regularity in order to break the curse of dimensionality. So in the context of physics, it will be to understand what kind of prior we can have on physical phenomena, so that given some data, we can build an accurate model of the physical phenomena, whether it's about learning energy or whether it's about learning the probability distribution of the state of the problem. So to try to move in the direction of this problem, I'm first going to begin by briefly reviewing some basic principle of machine learning and deep network. And one of the very important things that we'll see is that behind machine learning, there is this idea of trying to find the symmetries of the problem and linearizing the symmetry of the problem. And in that sense, we are not so far from the concept of physics. And what I would like to show is that this, in fact, builds a relatively natural framework for learning physics. And we'll begin with a statistical physics problem, which is learning the distribution of our data from the maximum entropy principle, which is the basic principle from which one builds statistical physics model. Now, one of the key ideas of the talk will be that the reason why it's indeed possible to learn from limited data, the reason why there is such strong regularity is due to scale separation phenomena. The complexity of the problem is not so big because one can separate scales, and that will naturally lead us to the use of wavelets. And in the last part, I will show how the same ideas applies to regression of quantum molecular energies. And many people have been working on that, so I'll be speaking about these works. Okay, so let me begin with machine learning in the simpler context. So a simple problem in machine learning, you have two classes of points. So you can think of such a point as being, for example, an image corresponds to dogs and a red point corresponding to cats. So you have points which belongs to two classes. And in your original space, essentially, it's a mess. It's a mess. The points have no clear separation. And the idea of kernel classifiers is that you try to find a change of variable that I write phi of x here. So this new variable is in dimension now d prime, in such a way that in this new space, the data is miraculously separated in two classes. What I mean by that is that in this new space, what you hope is that there exists a hyperplane which can separate the two classes. If that's the case, what you can do in order to find out which class you belong to is simply project orthogonally to the hyperplane. That means that you find a vector W which is orthogonal to the hyperplane, and you just project your change of variable over W, and you find whether you are on the left side or on the right side of the hyperplane simply by seeing whether the sign of the inner product plus B is above 0 or below 0. So it's very simple. It's very simple if you found this miraculous change of variable which essentially has linearized your problem. So the question is how to build such a change of variable. Now, you are in very high dimension, and in the original space, the frontier which separates the data may be extremely complex, extremely irregular, and the points are very far away one from the other in high dimension. So, as I said, what you hope is to find a change of variable which suddenly is going to do this separation. How one can think about linearizing problem. In math, this is a very classical problem. You have a set of, for example, nonlinear differential equation. You'd like to linearize them to compute the solution in a simple way. Now, the way to do that is to look at the symmetries of the system. So what are the symmetry of the system in that context? A symmetry is a transformation of x into a new point tx such that the value of your function doesn't change. F of tx is equal to f of x. In other words, here a green point transforms into a green point, an orange point into an orange point. Now, why is symmetries useful? Because if you have a change of variable which is going to linearize the separation, then you can view this change of variable as a change of variable which is essentially going to linearize these symmetries. Linearizing these symmetries means that these symmetries, what you'd like to do is to find a change of variable which is going to transform these symmetries in a locally parallel transport. If that's the case, then any change of data which preserve the class well corresponds to a parallel transport. So you can hope that the frontiers which separates the two classes is going to become flat, and then you can project. So there is really two stages. One is try to linearize, and then you have the projection. It's when you compute the projection that you compute an invariant. Once you've projected on that direction, then these points are invariant to any transformations of these symmetries. So the invariant is going to be essentially calculated from the data. And the priors will try to use them in order to try to understand how to linearize these symmetries. Now, two kind of questions arise immediately. First of all, how to design this kind of transformation which is going to miraculously linearize the symmetries.
What is f? What function?
Oh, f is the function that I want to learn. So f is, for example, the energy, and the symmetry will be the transformation that preserves the energy. Or f could be the function which associates to an image the label cat or the label dog. So what you want is to try to find the transformation which doesn't change this function f, okay? So supposing that you have some knowledge about the symmetries, the questions would be how to linearize or to transform them into something which is nearly parallel. And the key idea, which appears all over in differential geometries, basically is going to increase the dimension of the space by introducing so-called fibers, which will allow us to linearize the actions of these symmetries. But the problem is that we don't know the symmetries to begin with. We don't know the symmetries because we don't know f, and we just have some partial information. Okay, that would be, let's say, the theoretical point of view viewed from satellites. But then, since then, happened something is the remarkable success of these deep neural networks. So I'm sure that all of you have heard about deep networks unless you were living on Mars or some other planet, because we hear about them all the time, newspapers, companies, and so on. And the fact is they are quite remarkable. They are quite remarkable. These neural networks essentially are transformations which takes in input x. So for example, here I'm illustrating it as being an image, and is going to compute an approximation of f in the output, which I call here f tilde of x. Now, here there is an important contribution that was done by Yann Lequin, which was to structure these networks. And it is because of the particular structure of these convolutional networks that recently there were very impressive results for supervised learning. So let me briefly describe how they work. You have the input data x, and you are going to compute a first layer of coefficients simply by doing a convolution of here the image with a very small filter. Let's say 3 by 3 or 5 by 5 pixels in the case of an image, and different filters will lead to different images in the first layer. Now, the output, so the convolution is this operator, is also going to be transformed by a nonlinearity pointwise. For example, a linear rectifier, which will just take the maximum of the value of the filter output and 0. Then the next layer is going to be, for any of the image of the next layer, be calculated again by doing a convolution of each image of the previous layer with a small filter. And you're going to do a sum across all these convolutions. So you're going to have an interaction across what I'll call here a channel. All this is going to be summed, and you'll get the output. And these different images will be calculated with different filters that are going to be learned. And then you repeat the same thing until the last layer, which will be, let's say, my change of variable. And then finally, I do a linear combinations of the output to get an estimate of the function that I want to estimate. So how do you compute all these coefficients within a deep network? You optimize them so that the output on the examples that you know, the xi, is close to the true value f of xi. So you have a loss function, and you try to which express the total amount of error, and you minimize the loss function with a stochastic gradient descent. The miracle is that it works remarkably well in the sense that it generalizes. For many very large classes of problems, when then you test over data that the network has never seen, it provides good answers. So I say for large class of problems, it goes from image classification problem. The best image classifiers are essentially now based on that kind of techniques. You have face recognition systems which are better than the visual system. Speech recognition has also been revolutionized by that. All your telephones are basically working with that kind of speech recognition technique. Even language analysis, sentimental analysis, answering questions are based on such techniques. Biodata analysis, quantum chemistry regressions, many different types of problems are based on that kind of architecture, including playing Go. Now, what is very impressive is the generosity of that kind of architecture. How come is it able to solve such a very large class of problems, which in appearance are completely unrelated? So what kind of generic information is captured? Now, one thing which is important, and that comes back to the contribution of Jan, is that there is some prior information which is incorporated within this network. And the prior is essentially the architecture. How is the architecture organized? First of all, you have these convolutions. So it knows about translation, and in fact, you have operators which are covariant to translations. Also, you have this organization in channels. You have this succession of filtering, subsampling, these images are twice smaller, filtering, subsampling, and so on. So what does it do? It aggregates some information, and progressively it aggregates more and more and more information, so that a coefficient here really depends on a very large number of coefficients here. It essentially does a multi-scale transform, and this looks a bit like, in fact, a fast wavelet transform, although it's very different because you have all these nonlinearities that completely changes the nature of the problem. So there is some priors, and it looks like this prior structure is enough to learn this highly complex problem from a limited amount of data. One example in the range of statistical physics. So this work was done by Matthias Bege and his team. So the question is, can I build some kind of stochastic models of such images, including turbulence images, from only one realization? So what did they do? They took a network that was trained on a database of images totally unrelated to these images. They took one example of their random process, an image like this, decompose it in the network, and then for each layer of the network, they looked at the correlations between different images within the channels. So they built some kind of empirical statistics. And then how do they generate new example of their random processes? They generate new images which essentially have the same statistics with the gradient descent algorithms which optimize the statistics until it leads to nearly the same statistic. And the surprising thing is that with a lot of statistics that they carry, they get some realization which looks surprisingly good compared to the original one. The question is why? What's the underlying mathematics? This looks a little bit like magic. Okay, so let's come back to statistical physics. What is the key idea usually when you build a statistical physics model? You want to build a model of your probability distribution, and to do that, you are going to have moments, some observable about your system, which are basically expected value of some nonlinear functions or linear function of your state. And given these moments, you build a model by saying, I don't have any other information, which you express by saying that you are going to find a probability distribution which has a maximum entropy conditioned to these moments. So, question, what probability distribution satisfies these expected value and which has a maximum entropy? This is an optimization problem where you maximize a concave function under linear constraints, and you have this classic result which says if there is a solution, this solution has a Gibbs distribution form, so it's an exponentially of a linear combinations of your moments. Good, so if you want to build a model, it basically amounts in trying to understand what will be the appropriate moment to describe your probability distribution. In other words, how can you choose this function phi k so that the maximum entropy distribution is indeed close to your entropy, to your distribution that you want to study? If you take the log of the probability distribution, then you are going to have a linear expression as a function of your moments. So you get something very close to what we saw in the case of supervised learning, and you want to approximate the log of the true probability distribution as a linear combination. So question, how to choose these phi k? Now, if you know that, for example, your process is stationary, then p of x is going to be invariant to translation of x. So you have one level of symmetries, and that can be obtained by imposing that the phi of x are also invariant to translation. That's a basic property, but that's a very weak property. Other kind of property that you would have, for example, in turbulence. Observe that if these things deform, the probability that you are not completely destroying the structure. So the probability distribution is going to be very regular and potentially invariant to some type of deformations. So you know that this, you don't know what are exactly the symmetries, but you know that a very large class of symmetries will belong to the group of diffeomorphism, which we are going to deform. So one way you can try to think about these phi k is to try to build them so that they are going to linearize the action of a diffeomorphism, at least small diffeomorphism, so that to build an invariant, you'll just be able to do it with a linear prediction in your transform domain. So what people have been trying to do, the first kind of natural moments is to use second-order moments. If you use the second-order moments, then maximum entropy will give you a Gaussian distribution, and that's basically the Kolmogorov model of a turbulence. And you see that, yes, you get some level of regularity, but you've completely destroyed the geometry. Your model has much too much entropy. You haven't specified the geometry. So what people have been thinking is, of course, in physics, to use high-order moments and in statistical signal processing. And that's essentially a failure. Why? Because the high-order moments have a huge variance, are very sensitive to outliers, and you essentially can't estimate them and specify well enough such distributions. So what kind of regularity property can we use? We're going to use essentially principle of scale separations. So in physics, scale separation is very natural. When you study quantum physics, you don't have to worry about larger scale very often, and you try as much as you can to separate the different scale, which in fact correspond to different physical domain, quantum physics, chemistry, micro or biology, geophysics, astrophysics, and so on. Now, this principle, which is applied at these large scale, also applies when you study many body problems. One of the key idea which has simplified a lot the analysis of multi-body problem is in fact the ideas of multipole, which consists in observing that instead of looking at all the groups, you can regroup your variable. How? If you look at this particle, there is a very strong interaction with the neighbor particle. If you want to look at more far away particle, you can summarize the action of more far away particle with an equivalent field on this particle. Even more far away particles, you can regroup them in a bigger group so that the total number of interacting groups are not anymore d, but log d. However, when you have a nonlinear problem, the big difficulties is that all these groups are also going to interact. There are a lot of interactions across scales, and it may be extremely difficult, and that will be the challenge, to understand the nature of these interactions between these different groups. So scale separation, that will lead us naturally to wavelet transform. And what I want to show is that it's a natural path to understand why these deep networks make sense and to learning physics. Okay, so what are wavelets? The idea of a wavelet is essentially like a sine wave. It's a localized waveform. So think of a Gaussian multiplied by a cosine here for the real part and by a sine for the imaginary part. Now, this wavelet, you are going to dilate it by multiple factor 2 to the j. So you have your large wavelet. When you compress it, you get at different scales, you have these wavelets more or less compressed. And because we're in 2 dimensions here, I'm going also to rotate my wavelets, and these are the different rotated wavelets. Now, what is a wavelet transform? It essentially corresponds to taking the data and measuring the variation of the data with a convolution at different scale and along different orientations. So it's a convolution. In the Fourier domain, it's going to be a multiplication. And the Fourier transform of the wavelet is basically going to cover a frequency band. You can think of it as a frequency channel. When you rotate the wavelet, as we do here, you are going to rotate the support. Now, for all rotation, you are going to cover an annulus. And if you dilate the wavelet in the Fourier domain, it's going to be a dilation. And you see how you are then going to cover your whole frequency plan. Basically, you are exploding your information into multiple frequency channels, which are distributed that way. And if you build well your cover, then you are not going to lose any information about X. You are, in fact, going to have a unitary representation. But what is going to be very important, it's going to be stable to deformation. A small deformation locally looks like a change of scale, so a wavelet is transformed into something which looks very much like a wavelet. So how do you compute it? A bit like a network. You begin with your image. You have the different details corresponding to the wavelet coefficient in different scale. Black is 0, large amplitude in white. And you take the modulus here. And that's the blurred image from which you compute the next scale wavelet coefficients, next scale wavelet coefficients, and so on. So these are the wavelet coefficients. Now, we would like to build descriptors which are invariant to translation in order to specify, for example, a stationary random process. If you begin in one dimension, to make it simple, you want something invariant to translation, you don't have the choice if you impose to be linear. The only thing you can do is to average. So if you average a little bit, you are going to get a smooth function, a bit more invariant to translation. If you average completely, you get a constant. It's invariant by translation, but you've lost all the information. So the whole problem, of course, is to build invariants which are sufficiently rich in order not to lose the crucial information. So where's the information you've lost? It's the high frequencies. The high frequencies, you can capture them as wavelet coefficients. And that's going to give you oscillatory curves like that. If you average that, you get 0, so no more information. To get a new set of invariant, you need to apply a nonlinearity, and that will be one of the role of these nonlinearities in these deep networks. For example, you can compute the modulus. If you compute the modulus, then you get an envelope here. Now, this envelope is positive, so now you can average it, and you can have a whole new set of invariants. Now, because you've averaged the envelope, again, you've lost information. If you want to have something richer, more invariant, you want to recover the information you've lost. In other words, the high frequencies of the envelope. How can you do it? Well, you can do the same thing. You can extract the wavelet coefficient of your envelope. Why always using wavelets? Because you separate scale and you're going to get something which is stable to deformation, which you know is important for your problem. So in other words, you apply a second wavelet transform and again a modulus. So how does it look like? This is your wavelet transform, which takes, for example, the image and the different images at different scale, different orientation. And that's how it looks like in the Fourier domain. You've exploded your information along different channels. Now, after applying a modulus, you are going to reapply a wavelet transform. Like this. It's like taking this information and splitting it again after applying your nonlinearity. You do that at all, and then you propagate everything here to get an invariant to the last layer of your network. You do that for all scales and for all branches, and you are going to get a very large number now of invariants, which are all going to be at the bottom of your network, and the nonlinearity is what has allowed you to build more and more invariants. Then you can begin to do some math. You can try to look at the property of this operator, realize that it's a contractive operator because you've been applying a sequence of contractive operators. You can prove that it's stable. One thing which is important is, before I look at all that, you've built something which looks a bit like a deep network, cascade of convolution nonlinearities, but it's a very simplified deep network. There is in particular no connections between the different channels here. And we'll see what's the impact of that. And you have your continuity to the action of diffeomorphism that you can prove. If X is slightly deformed, you can prove that in a Euclidean metric, all these coefficients are going to have a movement which is of the order of the size of the deformation. Okay, so let me now go to the applications to statistical physics. So, suppose that you want to model a random field, like a turbulence, and I suppose here that it's stationary. Suppose that you take your image and you decompose it in your network. In the bottom of the network, you are going to get all your coefficients, which are basically the averaging of x, the averaging of x convolved with a wavelet modulus average, and then a sequence of several wavelets averaged. Suppose now that you have a very deep network. So the averaging is going to be very large. But if you have something which is stationary, if you have a little bit of ergodicity, a little bit of decorrelation, and you average a lot, this is going to converge to the expected value. So if the network is deep enough, you are going to average over a very large domain. What you are going to get at the bottom of your network is very close to moments, okay? And now you can ask, how can I use these moments to build a model of my probability distribution? Well, you can do exactly as we do in statistical physics. Try to build a probability distribution which satisfies these moments and which has a maximum entropy. And let me show the kind of results it gets. This is an image. This is the Gaussian model. So the Gaussian model consists in computing all these moments. You have d moments, and you compute the maximum entropy distribution. That's what you get. Same power spectrum. But it has lost the geometry. Here, the number of moments is the number of coefficients at the bottom of your tree. These are the scattering coefficients. You sample your maximum entropy distribution. That's the kind of thing that you get. You have much less moment, but you've captured all the interactions of scale and orientations. And that looks enough here. In the case of easing, you have a binary process with your a flip of sign, 1 minus 1, corresponding to the spin of a ferromagnetic material. This is the Gaussian model. This is the kind of model that you obtain with these same scattering coefficients by just putting your easing image at the top, computing the coefficient, maximizing the entropy, and that's the work which is done in collaboration with Johan Brunat. And then for turbulence. Well, if you look at turbulence, Gaussian is not great. This is a bit better, but not perfect at all. You see that you've destroyed some of the geometry. You get some of it, but there is too much geometry. For physics of bubbles, that's what you get. Again, you've lost information. So the question is, what kind of thing have you lost? Now, remember, in the case of deep network, there is these connections between the different channels. If we look at what we did here, we exploded the information at different scale, different orientation. We even refined each of them, but we didn't connect across angle or across scale. We didn't build all these connections. Now, these connections are very important because if you have any properties of invariance across rotation, connection across scales of structures, you haven't captured them or haven't captured them well enough. How can we capture them? Well, basically, if you have a rotation or a dilation, you are going to have a kind of transport in that space. If you want to build an invariant corresponding to the symmetry associated to this transport, what you need to do, same thing that what you did in space, a convolution along the angle theta, and potentially a transformation also along the scale. So basically, what I'm saying is the following. If you want to deal now with a bigger group, which is not just translation, but translation and rotation, now you have a group which is a bit more complex because it's a non-commutative group, but formally you can do the same thing that what you did before. What we did is we took the image and we built these wavelet coefficients so that now we explicitly created the variable of the group, which is the rotation variable. At the beginning, x depends upon the variable u. So you can act on translation. You cannot yet act on rotation. Now you created the rotation variable. So now you can make a convolution along this rotation variable. You can basically make a rotation along translation and rotation by respecting the group structure. And you essentially do the same thing than previously. It's going to be a convolution with a wavelet, but which now lives on spatial and rotation variables. And you are naturally going to connect, like this, all the rotation parameters. What about scale? Connecting the wavelet coefficient across scale essentially depends upon phase. So that's something which is a bit more complex. I'm not going into it. I'm just going to show you the maximum entropy model that you get by adding these coefficients, which you have in these networks, which connects scale and rotations. And what you have is this kind of maximum entropy reconstruction. You can see that now you've reconstructed the structures. Basically, they look very much alike. The number of moments that you have, now that we understand what is the underlying symmetries, are much smaller than the kind of the number of moments used by a deep network. It's about 100 times smaller. And indirectly, you've been building models of these turbulent structure. Now, in what sense these models relate to the physics, that's absolutely not clear, but you've been learning models from the data of these stochastic processes. Let me now go to chemistry. So, for chemistry, what you would like to do in quantum chemistry is to learn the energy of your data, your molecule, from examples. So what is the state of the molecule? It's going to be described by the charges and the position of each of the atoms, okay? And from that, you would like to compute the energy of the molecule. So that kind of topic has been essentially initialized by Gabor-Siani, Lilienfeld, Klaus Müller, and Alexander Tachenko, who did a very beautiful work around that, building database and trying to show that that kind of thing was indeed possible. Basically, what you want is to estimate f of x with some regression calculated from the input data where you have example of molecules and their energies which are associated. Now, why is this important? It's important because to compute quantum molecular energies requires to solve very heavy numerical calculations, including for DFT. If you could do that with a simple regression, then the applications are considerable in pharmaceutical industry for building new material, because you can explore much more configurations of molecules than what we can do right now with DFT. Of course, the problem is that you, again, have a high-dimensional problem, so there is no hope to be able to do such a regression unless you've understood what's the nature of the regularity of your problem. Okay, so what is the approach of density functional theory? So the idea of density functional theory is that instead of looking at the wave function of the n-body problem, you embed the problem into the electronic density. What I'm showing here are slices of these electronic density. What does it measure? For an organic molecule, a point here corresponds to the probability distribution of finding an electron at this position. So the probability is much higher when you are close to the center of the atoms, to the nuclei, and of course is non-zero in between, because that's the bounding, the chemical bounding between the different atoms. And these corresponds to 4 different molecules. So how do you compute that in density functional theory? That's the approach of Kohn and Sham models. You basically solve it as a variational problem. You express the energy as a function of the density. So you have one term which corresponds to the kinetic energy. You have one term which corresponds to the attraction between the nuclei, the electron, repulsion between the electron, that's the Coulomb repulsion. And you have this mixed bag of the exchange correlation energy, which corresponds to all the quantum effects. You solve the problem by trying to find the density which is going to minimize the energy, and you'll get the energy of the ground state of your molecule. So what's the machine learning approach? The machine learning approach looks naive. You are going to take this density, which you don't know. You are going to approximate it with a very crude density. And we're going to try to regress the true energy on some functional of this very crude density, which is going to hopefully linearize the kind of symmetries of your energy. So when you learn again the invariant, you learn this projector, and the physics essentially is there. Because here you've just done something which is very crude, and so the question is what kind of physics is captured by such weight if you can do the regression. And obviously, how are you going to choose these functions so that indeed the energy can be written as such a linear function? So to do that, same principle. To try to linearize, you need to have some information about the symmetries. What do you know about the symmetries? So observation of number of researchers in the area. First of all, obviously, you are going to have your molecules, which is described by their charges and their position. The energy doesn't depend upon the indexing. The energy doesn't depend upon rotations of the molecules. So your energy is invariant to rotation. It's invariant also to translation. So it's invariant to any rigid movement. Your energy is going to change smoothly if you just slightly dilate the molecule. So this energy is going to be very regular relatively to the action of diffeomorphism. And you know that there is some kind of factorization into local, and which corresponds to covalescent bond, and more global interaction like van der Waals forces, and hopefully that can be reduced as interaction of a smaller number of groups. Okay, let me just show you a little bit more specifically, in the case of the Coulomb potential, why it makes sense to do something which is multiscale. If you look at the Coulomb potential, it's going to be essentially a convolution with a potential which has a very slow decay and which is singular in 0, 1 over u. So the first reflex that you have is to think, okay, I have a convolution, so the best way to express this energy is in the Fourier domain. Why? Because the convolution is going to be a product, so this double integral is now a single integral of the modulus of the Fourier transform of the density multiplied by the Fourier transform of the potential. Now, the Fourier transform of this potential is still going to be singular at the 0 frequency and is going to have a very slow decay. So, if you want to evaluate this integral, you need, with an error, let's say epsilon, you need to sample your frequency very finely because you have a singularity here, so it has to be very narrow, but because you have a very slow decay, you need to go very far away, and the number of terms is going to be like epsilon to the minus 2. What you can do is something different. You need a very high resolution here, so you can sample very closely, but you don't need a very high resolution here. So basically, the natural axis is a log axis here. Basically, you can do a multiscale transform. And that's very well known. You have a singular integral which is homogeneous, and that's the basic reason why multiples are so efficient and can break the complexity to a log because you go in this multiscale domain. That's the same reason why it makes sense to compute wavelet coefficients to separate scales. So, what kind of wavelets we're going to use here? Here, we want to have something which is in 3D. So I'm going to take a Gaussian and the second derivative of a Gaussian. And I want to cover all rotations. So I'm going to do something which is in fact very similar to the representation of orbitals. For all the rotations, I'm going to use the spherical harmonics. So I'm going to use a wavelet, which is a radial wavelet, which looks like the second derivative of a Gaussian, and multiplied by spherical harmonics. Now then, these wavelets, we do the same thing. We dilate them, and you have some kind of multi-scale orbitals, okay? And all this is just inferred from the basic information that you have about the symmetry groups, which are invariance to rotation, importance of scaling. Then you compute your wavelet coefficients. The wavelet coefficient will consist in taking the density, compute the convolution with the wavelets at different scale. I take the modulus, and the modulus here consists also in summing over the M index so that I get something which is invariant to translation and rotation. Okay, now my problem is I don't know the true density, because to compute the true density, I need to know the whole variational problem, essentially solve the Schrödinger problem through DFT. And here I want to do it without any knowledge, essentially, of quantum chemistry. So I'm going to represent my density by a simple sum of Diracs. So I have a Dirac at the location of the atom multiplied by the number of charges. That's the amplitude of my Dirac. That's my very crude density. I'm going to use this crude density to regress the energy. Now, take a density like this. You have a Dirac multiplied by a charge. Make a convolution with a wavelet. A convolution of a Dirac with a wavelet is going to give you the wavelet located at the Dirac location. So it's as if each Dirac was emitting a wavelet. Each of these wavelets are going to interfere. If the wavelet is very small, the wavelets won't see each other. They are going to be separated. If the wavelet is big enough, they are going to interfere, and then you take the modulus, so you get the amplitude of this interference, and it's this amplitude of this interference which is going to capture the geometry. The geometry is captured through interferences between these different wavelets, and you are going to compute also the second order coefficients. I'm also putting a power q here because I need first and second order coefficient to get the Coulomb term. We're going to do that and then average, and I'm going, because I want something completely translation invariant, I'm going to average over my whole domain. So the average is going to get to become an integral. So the coefficients that I'm going to use to regress my energy are going to be simply the integral of all my charges, the wavelet coefficient absolute value integral L1 norm, same thing for second order, and the square, I'm going to get L2 norms. Okay? So these are the coefficients which are just derived based on the knowledge of the symmetries. These are typically coefficients that you compute with a deep network. Invariant by translation rotation, stable to deformations. Now, you take a database of molecules. So the database that most people are working with nowadays, this database QM9, which is about 130,000 small organic molecules, 29 atom maximum, and you take each of them, you decompose them through the scattering coefficients, so you get your interference patterns that you totally average, then you get your coefficients, and then from the database, you compute a sparse regression in order to approximate the true energy as a linear combination of your scattering coefficients. And what you're going to impose is to have something which is sparse. So you'd like to use as few invariants to try to regress the energy, okay? And the question, will it work? Now, if you look at the regression as the number of coefficients that are used increases, the error essentially goes back to 1.94 kilocalorie per mole on average. To give you an idea, the DFT has an error of about 2 kilocalorie per mole in this example relatively to the true chemical energy. If now you refine the regression, so if you have a deep net which learns, there have been people trying, you get an error about 0.45 kilocalorie per mole, but you need a lot of training data And again, DFT has an error of 2 kilocalorie per mole, so I don't know whether it's worth to go so down. But you can do the same thing with these invariants by just doing not a linear regression, but a trilinear regression, and you can get the same kind of error. What is important is that if you use a simple linear regression, you can learn from much more limited amount of data. Instead of using 100,000 example, you can just use 1,000 example and get about 2 kilocalorie per mole. So that shows that if instead of just learning blindly by letting your network learn everything, you put a little bit of prior, which tells you mathematically, well, the filter should be, in that case, wavelets with all the rotation properties, you can reduce considerably the amount of data. Now, scientifically, the questions are totally open because we don't understand why we are able to regress this kind of energy. In what sense is that related to the property of the underlying Hamiltonian? In what sense is that related to the property of the Schrödinger equation? From the point of view of numerics, all these experiments right now are done on small molecules. So the question obviously now is, will it scale to much larger molecules? Are these things sufficiently efficient to really attack real life problems as you encounter in pharmaceutical industries or in material sciences? So let me conclude on all this. The first thing is deep networks are remarkably efficient, not only for physics, but for other problems, but they have prior information. And in that sense, they are related to the underlying problem because the architecture, which is multi-scale, which imposes convolution, already expressed prior information about space, translations, and scale separations. Now, in general, in machine learning, you have this prior information which allows to define a nonlinear change of variable. And then the data basically is used in order to do the projection and to, in other words, build the invariants. So in that sense, you are learning the invariants of the physical system. Yes, you are not learning the fundamental equations, but you are learning a very important information about the system, which is this invariant. Can this be called learning physics? I think so, even though, again, you don't have access to the fundamental equations, but I let to the physicist decide whether that's called physics or not physics. Now, if you want to try to relate the physics and the fundamental equation to machine learning, it's very hard to do it if you have to learn everything in a deep network which is completely unstructured. And this is why, in that kind of thing, you want to try as much as you can to understand in what sense the symmetry of the problem allows you to specify the filters and therefore to specify this nonlinear change of variable. Now, the question is, can you do that as well as you can do when you learn? In the case of quantum chemistry, until now, yes, you can. You don't need to learn the filters. You can infer them from mathematics, and in that case, use wavelets. If you look at more complex problems, such as image classification, it's wrong. Right now, learning gets you much better results than specifying the symmetries. The question is whether it's not possible to do it or whether we just don't understand right now the mathematics well enough. In the case of physics, at least, I think it's important to try as much as possible to remain with representation which are well controlled from a mathematical point of view. Now, one thing I didn't speak about at all is the issues of time evolutions, which obviously is extremely important. That's the kind of questions you'd like to answer if you want, for example, to do prediction in meteorology. Number of people are working on that. Can we have that kind of dimension reduction techniques be applied to specify properties of solution ahead in time? Numerical experiment seems to indicate that there are promising things to be done, but again, here the mathematics are extremely unclear. Now, in general, you have a good knowledge of the physics of the many-body problem. You have a knowledge of the Lagrangian, which specify all the interactions. And now you have these machine learning techniques which arrive from the top, which specify these invariants, which seems to be able to linearize the problem. Right now, there is no connection between the two. We don't understand in what sense this linearization occur, why is that, where does it come from? In what sense it relates to the property of the Lagrangian? And again, there are many things to be done around that kind of topics. And I'll finish that, it's just 0, 0, 0. Thanks very much.